Hey, Katie.
Hey, Ben.
So we talk about a lot of different algorithms on the show, and it seems like all of them have certain strengths, and then they also have certain weaknesses. And so it got me thinking, is there a way that we can, in a sense, bring these strengths and weaknesses together to create an ultimate model, which perhaps we can have more strengths and fewer of the weaknesses?
Well, it sounds like you might be talking about something like ensembling. So, yeah, let's talk about that.
You are listening to Linear Digressions. So, ensembling, is that what you said?
Yes. So, ensembling is not even really exactly an algorithm. It's more like a meta algorithm, almost, I might say. So, the idea is you build a bunch of models and then you come up with some way of combining them at the end. And so, even though each one of these models might have some problems with it, it might not be perfect, the goal is that the ensemble, the bulk of them taken together, is going to be, in general, better than any one of them individually. And so you can get actually really strong classifiers out of these kinds of methods. Classifiers and regressors, I should say.
So if the idea of ensembling is taking different models and somehow smushing them together so you get kind of a synergistic, greater than the sum of its parts thing going on, can you take any model and smush it with any other model?
Oh, well, I suppose there aren't any laws against that, obviously, but usually in the kinds of ensembles that I'm thinking about, they're usually built on top of decision trees. So you build a decision tree, which is a certain type of algorithm. Usually it's just sort of a binary tree that'll make cuts on all the different variables sort of sequentially and in this recursive way. And so each decision tree can be imperfect, like we said, but if you build a whole bunch of them and then you combine them in, there's a couple of different ways you can combine them, actually. The first is that you can average them. So you think of each one of your decision trees as independent of all the other ones. And this is nice because you can parallelize this really easily, so those tend to be really fast algorithms.
Right, so because they're independent, let's say your computer has 16 CPU cores or something like that, you could conceivably run 16 different models all at the exact same time, and they all finish in, let's say, 10 seconds rather than just one model finishing in 10 seconds.
Yeah, that's right. So it can be quite fast to run these kinds of models. And then at the end, you bring them all together, and usually there's some kind of voting process. So if you have 16 different decision trees and 10 of them said, I think this particular example was class A, and 6 of them say, I thought it was class B, then usually, class A is the one that it settles on.
In a sense, you kind of pit them against each other and go with a majority vote or something.
Yeah, that's fair. And then the second one is what's called boosting methods. And so the idea with boosting methods is that you have sequential learners. So the first decision tree is built, it makes some mistakes, and then the second tree that you build hopefully is you in some way sort of pass the information along to the second tree. Hey, here are the things that we were getting wrong before. Pay a little bit more attention to those examples and see if you can do a better job. And so hopefully decision tree B makes, it might not make less mistakes, but at least it'll make different mistakes. And so then when you combine them at the end, hopefully it's starting to get a little bit smarter about which examples are the hardest to classify, and it spends the most time on those ones.
That's really cool. So you're basically using earlier models as a way of figuring out how to focus your later models. So you get ideally better at the harder problems.
Yeah, that's right. So I think it's also worth talking about a few of the specific algorithms, calling them out by name, that are the most popular within this sort of umbrella of ensemble models. In particular, I think it's worth talking about these because ensemble models are some of the models that tend to do best in places like Kaggle or, different kinds of benchmarking competitions and things like this. If you have to run a classifier or a regressor sort of out of the box, you don't know anything about the problem that you're dealing with, and you just need to make your first initial best guess, an ensemble method is actually not a bad place to start. So they're worth knowing about. So with that, let me jump straight in. I've taken most of the material for this episode from actually the scikit-learn documentation, which I think is really, really good. So as we explain these algorithms, there might be sort of small variances in exactly the way things get implemented. So this is the scikit-learn flavor that you get, but the general idea will come through. So the first one that I want to talk about was bagging. So the idea is that then you take your training data and you actually take random subsets of your training data. So each one of this is an averaging method. So these are the trees that you can run in parallel. Each one is independent of the other ones. And the idea of bagging is that you actually use slightly different training data sets in each one of the trees that you use. And each training data set is sort of a subset of your full training set. So if you have 10,000 training examples, each bagged tree might draw 7,500 of them with replacement from the original 10,000, and then you train on those. Bagging is something that I think I heard more about maybe 5 years ago or so. This isn't an algorithm that I hear about quite as much today. So on to the second one, which is one of my personal favorites, the random forest.
The random forest. I somehow, that sounds familiar to me.
Yeah, this is one of the big ones. First of all, the name comes from the fact that it's built out of decision trees because it's a forest and forests are made of trees.
Oh, clever. You data scientists.
Yep. And so the idea with a random forest is that often you're doing a similar thing as bagging. You're using a subset of the data to train each one of your trees. But a random forest also will only look at a random subset of the variables at any point when it's trying to decide which variable it wants to make a split on. So the idea of a decision tree, like we said at the beginning, is sort of a binary tree where you might split the data on one variable, and then if you have, let's say the variable that your decision tree splits on, you're trying to tell if someone is a man or a woman. And so the first split is going to be, is this person more than 5.5 feet tall? If yes, then go to the right, and if no, go to the left. And then for people who are taller than 5.5 feet, you might say, is this person wearing high heels? If yes, go to the left. If no, go to the right. And so on. And so how tall the person is, whether they're wearing high heels, maybe there's variables about how long their hair is, or whether they're wearing makeup, or all these other things that, what their name is, all these other things that you might use as clues to tell what someone's gender is. All these variables might be available to you in your data set, but a random forest will only pick a random subset of those and at any given point only draw from that random subset when trying to make its decision. So it's actually each tree is ignoring part of the data. But again, taken together, all the data is accounted for. It's just that each one gets kind of like this weird, different half picture of what's going on.
So bagging and random forests seem like they're kind of centering around the concept of averaging. What are some of the other kind of methods?
Right, the boosting methods. So these are the sequential ones where each tree tries to be smarter than the one that came before it. So there's two that I want to talk about here, which is adaptive boosting and gradient boosting. They're actually really closely related. So the idea of adaptive boosting or AdaBoost is that
nice.
Yeah, is that so you have tree A and you build this tree and it's going to make some mistakes. There's going to be events that it misclassifies. And then those events get upweighted. So instead of counting each event that you misclassify with a weight of 1, maybe you change it to have a weight of 2 or 3 or something. And then that data set gets passed along with the new weights, gets passed along to the next tree that gets built. And so that tree now, because each time it sees something that it missed before that has this big weight now, is going to try extra hard not to misclassify it again. So it's going to learn a slightly different version of the model that it's trying to build. That version of the model will itself make some mistakes. Maybe they're new ones. Hopefully they're new ones, but sometimes they might not be. Upweight the ones you miss, pass it along to the next one in the row, and so on like that.
Right. So you're kind of adaptively compensating for your mistakes by focusing on those areas more, by weighting them more heavily.
Yep. And then gradient boosting is kind of a supercharged version of the same idea. So gradient boosting actually defines a loss function. It says that, let's imagine that there's some perfect classifier that exists out there in the world, and that's what we're trying to learn. And what we have right now in hand is a maybe a reasonably good model. It's this decision tree that gets a lot of things correct. But if you imagine there's like the perfect model and there's the model that we have, and there's kind of this gap in between them. And so what gradient boosting tries to do is it defines that gap in kind of a functional form, and then it tries to minimize that function. And it takes advantage of gradient calculations, basically, to try to figure out which events it should upweight and by how much. So again, it's the same idea, but it's a little bit more formal with respect to exactly the way that it defines the problem. It defines it as basically an optimization problem. And so that can be very, very effective at trying to minimize kind of that gap between your hypothetical perfect classifier and the classifier that you're actually building.
So given that we've described these in like 10 minutes and 4 methods as well, it feels like they're relatively simple methods. Do they really do that well? I mean, you said that they're good to have in your toolkit, but are these like when you're getting into it, when you're more of a beginner, you want to pull these out? Or like do seasoned data scientists use these regularly?
Yeah, all of the above.
Really?
I think they're great. Yeah. I think they're great for beginners because some of them you do need to tune the hyperparameters a little bit before they work well. They're not totally foolproof, but they tend to do really well on a wide variety of problems, which is really nice. You don't necessarily have to have, there are lots of algorithms that kind of have underlying assumptions about, well, if the data is like this, then this model will do well, or if the errors have that distribution, then this model will capture that correctly. These methods tend to be more robust against all those different kinds of weird things that can happen. So you don't necessarily have to have perfect data sets or even data sets that you have looked at from every which way that you understand perfectly in order for you to have a decent chance of getting some good results out of these algorithms. And then for the people who are, a little bit more advanced or the more expert level, these algorithms tend to do really, really well in competitive environments as well. And a lot of the benchmarks, what are some of the best out-of-the-box algorithms for certain standard problems? For a long time, it was gradient boosting. In fact, for a lot of problems, I still think that the best classifiers are simple gradient boosters. So it's not just that they're fairly straightforward to get started with, but they actually will take you really, really far on a broad range of problems.
Linear Digressions is a Creative Commons endeavor, which means you can share or use it any way you like. Just tell them we said hi. To find out more about this or any other episode of Linear Digressions, go to lineardigressions.com. And if you like this podcast, go ahead and leave us a review on iTunes so other people get to listen to this content too. You can always get in touch with either of us. Our emails are ben@lineardigressions.com and katie@lineardigressions.com in case you have comments or suggestions for future shows. You can tweet us at lindigressions. Thank you for joining us, and we'll see you next time.